here today.
It's gotta be probably somewhere in email threads.
I've looked through every email. I've gone through the zip files and everything.
Gotcha. I've heard just cut that last quite a few times.
I may,
Yeah, she's probably the most likely to.
I'll email her after class.
Okay.
I see now you've got two people.
There you go. I was just telling it has been ages since
In person,
having in-person submittals. Rob used to do that, but I think it seems like it was last semester.
At the end of the semester especially, you just got everything.
But everything there, yeah. So,
And there was one homework that I finished early and I was so excited that I scanned it and sent it to you because I had it done 2 days early.
how are you?
Hello, doctor.
Where are others?
We got our first assignment for quantum mechanics for the weekend.
fun.
So I have no plans this weekend except for
Gotcha. What are you starting with?
He's got us doing some matrix stuff. So, I mean, it's not going to be hard, but there's 8 problems.
Oh.
So, and I also have to figure out how much detail he likes.
Mhm. Are you in a particular chapter in balancing?
We actually haven't even discussed the textbook other than there is one.
Gotcha.
And
Okay.
I ordered a hard copy of it.
Mhm.
And I have the download, but I've got the newer edition.
Yeah, I went ahead and got the hard copy as well.
Well, there was only like $6 difference between the hard copy and the paperback.
Yeah.
Yeah. Oh, Jordan's cloned himself.
Jordan, you there? Probably not.
I do wish we could talk Dr. Bird into using Zoom versus the virtual classroom.
Is Zoom better?
I think Zoom is better. The first two class periods, the first 15 minutes were technical issues.
Yeah.
And he still couldn't get his pen to work. Everybody else's pen worked.
Oh, it's only his site. It did.
Is only the person running the
The host.
meeting couldn't write it.
Huh.
I'm not a fan of D2L.
Yeah, I don't know. I haven't used it, so I cannot say. Yeah. Hey, Jordan, give me a couple of. I'm trying to figure out because now I need 8 of them, right? So I'm trying to figure out a convenient way of doing this setting.
You need 8 of what?
The presets
Removing the board.
for moving the board from, earlier it used to be only 2, so now I need a double digit ways, I guess. Or I have to remember if it is 8, I usually keep 2 here, 2 here. So I'm just, I'm doing this double digits, but I'm all confused now. Let's see.
Now there's just one Jordan. There were 3 of you up there.
So
That's weird.
how was the homework?
Wasn't bad.
You got used to long homeworks now?
It wasn't too bad.
My homeworks kind.
I tried.
I think that's one problem with you taking many courses with me, right? The style remains the same kind of. Right? So you guys don't get to see much other styles of courses. Kind of.
I tried to shorten the problem too, but you weren't having that.
Alia, how are you?
Good, thank you.
Your kids don't have simultaneous classes this semester, huh?
Yes.
Okay, I think I got this one side done. That's it now. I did get a round tip though.
Hey, Rob, did you ever figure out about the lecture video for 253B? Because I was looking for 255B, which I'm guessing is the same video, but I didn't find one either.
I'm gonna ask Prova,
Okay.
because Tori's either he's gone to lunch or he's not here today. I'm not sure. I told him I'd extend the deadline for however long it took me to get the video posted.
There you go.
Once I get it, I'll send it to you.
Thank you.
Does anybody else need the B information?
I just need the 255B. That's not that. Usually they send them together, I think. That's how they did it the first time I taught the class, but not good.
The only thing that I found was the sketch of the magnetic field lines of a bar magnet that Scott did.
Sketch.
Because I know one of them you're supposed to do
Yeah.
that was the only information that I found. And so I told them to go ahead and start setting up their lab report with the information from the lab manual, and I would get the information.
It's probably a good idea. My lab isn't technically till Friday, so I guess as long as I have it uploaded by Friday, I think I'm okay. Because I'll still have a week to do it.
Okay. Is that all your presets?
Yeah, double digit.
Nice.
Let's see if I remember it down the line. No. Already I'm in trouble. No, that's okay. Okay, so there's a homework. Two. Oh, I did get round tip. Let's see how it works today.
Oh, okay.
So homework two. Due February Tuesday. And midterm one. Two. I just realized I was talking to Rob. I think I should tell you guys too, because I think you guys with some interest in it. I had mentioned last semester that I will request or we should request for a camera for this room from the university, because the university gets money for this federal grant. So it's a pretty big money amount. So I did write to them, and after a week or so, they did give a very nice response. So I basically showed them some videos, what we do, and they were very happy about it. The first response I got, this is very nice. We are glad and everything. We would really like to support you. And I was very excited. And I said, yeah, so this is what I do. This is how I added on to it. But then in all the discussion by the end it came about, so what happened to the camera in the last semester? So I said, I still have it. And then they said, oh, then we cannot do that because it's upgraded. So they have this apparently the rule that they would like first try to help others, presumably help others, but don't have anything and then come to this. So everything fell apart.
Sucks.
Yeah. So the wrong move. Don't tell them. But I wouldn't say wrong move, but that's yeah, that's what it is.
They're like, great work, keep it up. We're proud of you.
Yeah, that's right. Even they're even, oh, you should make a tutorial. We would like to advertise this so that others know about it. And I said, yeah, I will be ready to do all that.
You should tell them your camera's not good.
I need to learn all these things. Yeah. So yeah, I didn't take too much interest in making the tutorial after that, and they probably did not bother to, or they probably didn't feel good to ask, I suppose. Yeah, I don't mind making it. I'm not against them at all, but it's just that it took me up and then dropped me. Yeah, but that's what happens. In fact, I also had to move one of the classrooms to another building. So these are adding the whole thing to another building and bring it here because, oh yeah, because this room also has the problem of number of students being more. But yeah, I'm just ignoring it. I think I did get things in writing from you guys, right? You guys all right? I mean,
About the occupancy?
yeah. I think some of you guys, if you are not, to write that helps.
I think actually we are within the occupancy now. Well, no.
Now, Michael might be here, right? 1, 2, 3, 4, 5. We have 6 and enrollment of 6 actually. Yeah. And 6 plus me, 7, and that comes with 6. So some liability to the extent that they moved me out. So that's a little, yeah, it's a little inconvenient, but not.
So I found an option in Zoom itself, like on if you go to your computer screen on the video part at the bottom left corner where it says like your
Video?
mic is active, and then there's the stop video option.
Yeah.
There's like a little caret key. If you
Yep.
click that caret key, you can go to video settings.
Yeah.
And there's an enable HD. Do you have that?
Let me see.
It is on.
Okay.
Oh, here, enable HD. Yeah. So it is HD, but we don't see HD, is it? Like our claim is that the videos are not coming out HD, right? At
Yeah.
least it doesn't seem like.
Yeah, that's what it seems like.
Okay.
image that I'm seeing up on the screen, I mean, I can read that
Pretty well, yeah.
fairly well from here.
And we are also on the internet, right? It's going and
Yeah, I
coming
think
back.
that's where there's a lot of loss happens is.
Oh, yeah, you're saying this is direct, right? This is not going to the internet.
Yeah, what we're seeing is,
Immediate, is it?
I think so. I'm not 100% sure, but
So there's probably nothing you could do with the camera unless you got like a 4K.
Well, I don't
Well,
even think that. I don't think the camera is going to matter as much as just enabling an option, because I kind of read about it a little bit, and there's, depending on which license I suppose that you have for Zoom, you're restricted in what your prerequisites are for like the group HD.
Oh, is that the problem? I mean, because Jordan has been telling me that, and probably he's correct because I did go and look into it. It seems like he is correct that the last spring, the videos were much better than this.
they're trying
Oh,
to show us something.
Yeah. Oh, I was missing that.
Oh,
But Jordan, you just mentioned that license. I have been using I was using my personal account in the last spring. And since fall, I'm using the university account.
Okay.
Do you think that could be the?
So it says it depends on, I guess, what you have for, they call it prerequisites. And if you have like pro or business enterprise account, you can get 720p. But if you have a business, education, or enterprise account, like I guess the accounts are different. And I'm assuming that if you use the Zoom license that the university gave you, it would be education. You can get full HD 1080p. So
It should be better, right? But we are seeing the opposite.
yeah. So if you're on the license for the university, if they do indeed have an education license, which I'm assuming they do, then
One of these days we should experiment it on the other room. Today, I think we've already lost some time. Let's not do that. Yeah. It's just easy, I think, because you guys do use it, right? I mean, you guys
go back and look at the lectures, you mean?
No, I mean, you guys use my personal account for that student, what is it called? Student launch that we created,
Yeah.
Moses?
We use it occasionally.
Yeah, so that works, correct? And
Yeah.
I also use it once in a while, yeah. So you guys know the access, I don't remember it, but it should be there. Yeah, okay, we should be able to do that sometime, yeah, okay. But that's not really, okay. Double. Okay. We started on discussing the magnetic field due to a straight wire. Usually magnetic field due to a straight, infinitely straight wire is the simplest magnetic field you can think of. A current carrying wire, magnetic field goes around it. But often in introductory physics course, we don't talk about the electric potential. Sorry, not electric, magnetic potential. So that's something we should do. And what's the related concept? So that's what I want to do here. So let's say straight current carrying wire, straight wire. So let's say this is on the z-axis and it's a finite wire. So this is this coordinate here is x equal to 0, y equal to 0, and let's say this is L2, and this coordinate here is 0, 0, L1. 0, 0 means that it is on the z-axis. It is not equally spaced from the origin, so it could be somewhere here. So that's 0, 0, 0. That's your origin, and there is a current I going through the wire, and we would like to know, actually, I should, but now let me just say this is position or observation point. But we also said if we want to satisfy the equation that the current density is divergence-less, that was necessary because magnetostatics requires that. This requires that magnitude of R is very much less than L or L1 or L2. L1 or L2. So you got to be close in this region. So even though I showed this R, we are too far. So we cannot really go to infinity because otherwise we will be violating for that. So whenever we are doing a straight wire, keep track, be aware of this implicit assumption. What is the current density due to this wire? It is in the direction of z hat. That is a current I, and current density is current per unit area. By area, we mean the cross-sectional area of the wire in this case, and that's given using the delta functions, right? Delta function has inverse length, so it is a very small area. And this time, let's say this is prime, and delta of y prime. That will be current per unit area, but we also have to put in the information that this is finite, and in that case, this is L1, Z prime, and L2. If it was really infinite, then you're good, then we don't have to worry about this. But since it is a finite wire, then that's required. Okay. That's the information we need, and we do know that two information, right? There is vector potential at an arbitrary point R. Like we have electric potential, this is magnetic vector potential, is given using the superposition principle of current densities. Very similar to electrostatics. In electrostatics, you would have written this as electric potential. This would have been charge density, and instead of mu naught, you would have had epsilon naught in that. Once you have the vector potential, magnetic field is given in terms of the curve. Or there is an expression for the magnetic field itself using an integral. That's the Biot-Savart law. Right? And we will do both ways. First, let's do it this way. And let's substitute this. So this is equal to u naught over 4 pi. I still, oops. For the time being, I'll put it in. So that's minus infinity to plus infinity dx prime, minus infinity to plus infinity dy prime, minus infinity to plus infinity dz prime, and then there is z hat I. This in principle is z prime hat, right? We're working in z prime, but z prime hat and z hat are the same. They are not coordinate. So in principle, this is z prime, but that can come out. Like it doesn't change with z prime. So that's I delta of x prime, delta function of y prime, and then there is theta of L1, z prime, L2. And this is x minus x prime square plus y minus y prime square plus z minus z prime square. The whole square. the delta function integrals are immediate. Z prime is the same as the hat itself. Bring it out. It doesn't depend on Z prime. So this is Z hat mu naught I over 4 pi. Complete the x prime and Z prime integral. And notice the Z prime, because there is a limit in here, this function says that it is equal to 0 if you don't satisfy that relation. So if it is 0, that means you can, it puts a limits, constraints that integral. So it goes from L1 to L2. So this is Z prime. All the numerator parts are done. It's equal to x squared plus y squared plus, let's write this as Z prime minus Z the whole square. Like we started on this last time. X squared plus y squared, it's convenient to write it as rho squared. That's a cylindrical coordinate. Let's substitute. Z prime minus Z is equal to rho times sine hyperbolic of theta. Substitution. There, what is rho here? It's good to bring that out in this diagram. Oh, this diagram may not be. So in this diagram, that's your rho. That's your rho, and this is your Z. So any arbitrary point, and yeah. Yeah, let's also at this point point out that if you were to do this, then this distance is Z minus Z prime, right? Or Z minus L1, right? If L1 was less, notice that I have written L1 randomly here. If L1 was less, it is understood that this is negative. So this is Z minus L1. So what am I saying here? Do I have an implication there? L1 to L2. Let's say, yeah, let me be specific here. L1 is less than 0 and L2 is greater than 0. Okay, let me keep it that way. That's an understanding that then this becomes plus, right? So that's Z plus L1 and we have Z plus L1 divided by rho. Z plus L1 divided by rho of what is my I need some help here. So okay, let me not say anything.
I think that distance is still Z minus
Yeah, I think it
L1.
should still be Z minus.
Z minus of,
Yeah,
because this is Z, right?
Right.
yep,
And that's L1.
yep, which is negative.
But L1 I said is positive now.
No, it's negative.
You said it's
You
less than
you
zero.
justify it as being negative, so.
I will give it to you then. Okay. Because you're saying, oh, because L1 is negative by number. Yeah. Okay. Plus, yeah. So, yeah. I'm more bothered about this angle theta. I was trying to capture this angle theta in here, but apparently this is sine hyperbolic. But we'll come there. Okay. As we go. I thought I will capture this as some angle there, but apparently not. So, yeah, okay. Because typically that answer can be written as. Yeah, let's not worry about it. Yeah, I think. How about this? I'll keep this as 5 because maybe some later on we'll have something. Okay, so that's angle 5 sine hyperbolic of 5, and we immediately have dc prime is equal to rho cosine hyperbolic 5 d phi. Correct. Okay, so that's equal to. So you have mu naught I over 4 pi times, now when z prime is equal to L1, we have L1 minus z, so that's sine hyperbolic inverse of L1 minus z over rho. L1 minus z. Yeah, actually we do get that, right? So it's coming out in the right form. Okay. And on the numerator or in the upper limit is sine hyperbolic inverse of L2 minus z over rho. dz prime is rho cosine hyperbolic phi d phi, and in the denominator we have rho square plus rho square sine hyperbolic square phi. Correct. 1 plus sine hyperbolic square is cosine hyperbolic square. Yeah, and it has a square root. So this whole denominator cancels everything in the numerator. So this whole thing cancels out, and it's a trivial integral d phi, and that's equal to pi over 4 pi times sine hyperbolic inverse of L2 minus z over rho. Z and rho are, remember, the observation points, right? Z coordinate of the observation point rho, and L2 is the parameter of the wire. Minus of, instead of writing what did I mess up here? Yeah, that's what I wanted to do. Shall I change now? Yeah, that's what I think that's what I was trying to do here so that that comes out correctly. Yeah, let's say L2 is positive quantity, L1 is positive quantity, this is minus. Okay, so then this is plus. I think people are not seeing that there. Okay, again, I said this is a positive quantity, C. This is also a positive quantity, so I'd say this is a minus of that. So I'm purposely putting it on the negative side, I suppose. Yeah. Am I going to lose anything like that? Give me a second. Yeah, well, let me keep it one below and one above, right? L1 is below, L2 is above, so this is positive. That's not the important one. Here, then I would put this Z prime is minus L1, right? So the L1 is a positive quantity in that, so that's very, since I confused you guys, let me put the magnitude there. So that's L1 and L2. So this is magnitude of L2, and this is minus of magnitude of L1. Right, so this is magnitude of L2, and now I can pull out a minus sign out, so that makes it a plus. So this is sine hyperbolic inverse of L1 plus Z over rho. I need that plus sign out. I'm foreseeing something coming, so I want that plus sign. It doesn't mean that this wire cannot be completely above the origin. It can be, but then typically you work around the origin, right? So if you move it above, then you have to place restriction on your row there. So it's good to keeping our approximation in mind. It is good to keep. Okay, good. Any questions, comments? Will I move my time? Okay. If we know the properties of sine hyperbolic, we can immediately work with this. We can take limits. We would like to talk about situations where Z and rho are very small compared to L2, but offhand, I don't remember it, so it is good to put it into something that you know, so that is log, right? A logarithm, is all the hyperbolic functions can be written in terms of logarithm. And so let's say y is equal to sine hyperbolic inverse of x, right? So that's the function we are interested in. Invert it immediately. That's y is equal to x, but this is e raised to y minus e raised to minus y over 2 is equal to x. That's exponential of y minus exponential of minus y is equal to 2x. Multiply it by e raised to y. That's 2y squared minus 1 is equal to 2x times e raised to y. That's a quadratic equation in exponential of y, which has the solution out of the, no, still, which has a solution is equal to 2x plus or minus 4x squared plus 4 divided by 2, which is equal to x plus or minus x squared plus 1. So we take it the logarithm on both sides, we get y is equal to, so y remember was sine hyperbolic x, right? So y was sine hyperbolic inverse of x, which is nothing but, that's another identity. So it is, you would say it is plus or minus, it could be both, but notice that log is not well defined for negative numbers, and this could be larger than this, so you take only the positive. So it is x squared plus 1. Okay, so that's a identity for sine hyperbolic inverse. Once we have sine hyperbolic inverse identity, you can actually plug that in the expression we had for our our vector potential. So that's equal to, so vector potential A of r is equal to z hat times mu naught I over 4 pi times sine hyperbolic inverse. Instead of x, it is L2 minus z over rho. So that's logarithm of L2 minus z over rho plus the square of that. So it's L2 minus z over rho square of that plus 1 square root of that. It's a messy thing, but we are going to take the limit very quickly. So all this is going to get very we'll be able to drop out many. We are adding things. So there's one more term. Plus one. Okay. That's a vector. That's a closed form vector potential for a finite wire segment. But again, we should remember that because current has to, or charge has to be conserved, our currents have to be divergence less, and that requires that Z should be small compared to L1 and L2, and rho should be small compared to L1 and L2. I mentioned it sufficient number of times. In fact, why not take the limit? Like, since it's small, take the limit where Z and rho is small. So let's take, if we are to do that, we have to actually take one piece out to begin with. So let me, allow me, I'm going to go up instead of going to the new board. Let me move upward. Okay, so this is equal to, I think I can do this. So this is equal to, in the upward direction. So since I need two lines, go further up. So that's equal to Z hat U naught I over 4 pi I pull out an L2 over rho from here. So that's log of L2, magnitude of L2 over rho. Pull that out. And remember that log of A times B, product of log of A times B is sum, right? So I can write, so this is just the first piece itself. I'm going to write that. And the second term, I'll pull out a log of L1 over rho plus log of something. What is it if I pull out L2 over rho? Whatever is remaining is 1 minus Z over L2, magnitude of L2. That's first term. That's this term here. When I pull that L2 over rho outside, is that clear? Ask me if I'm doing too many things simultaneously. And same thing here. I've taken an L2 over rho out, so that's 1 minus Z over L2 square. And now 1, I've taken an L2 over rho outside, so it is rho square over L2 square. And I can close this. Is that visible on the online site? Probably. I can, yeah.
Yeah, I can see it fine.
Okay, good. Okay, good. Same thing in the next term. So it's 1 plus Z over L1 plus 1 plus Z over L1 and then close the whole bracket. Okay. Okay. But these are all small quantities. The way I wrote it like this is that it's very clear that if this approximation is true, Z over L1 is small compared to 1. if I divide this out, z over, so our understanding is that z over L1 or L2 is very much small compared to 1. So if it shows up with 1, I can neglect it. Right? Same thing with rho over L1, it's very much smaller than 1. So whenever it's in reference to 1, I can drop it. So this I can drop because it's 1 minus of something, they're really tiny. This I can drop. Right? Once I drop this is 1, I can drop that also. Right? And it goes through. I cannot drop this because it is not coming with 1. Right? So this has to stay. So what is remaining? There is a 1 here, and there is a 1 inside of the square root. So 1 plus 1, 2. This is the logarithm of 2. So this is equal to, z hat mu naught I over 4 pi. Yeah. Log of L2 over rho plus log of L1 over rho plus log of 2 plus log of 2. Right? After taking that limit, like you're saying, we're very close to the 1. Okay. Which means our A of R is equal to, I can put this all together, right? So this is this times this times this times this, right? So typically the way it's written is up. I guess, let's see, I don't remember, but okay. So this is 4 pi, and then I have log of L1, L2 over rho square, right? And what is this? Flow like this, right? Right. Yeah, L1 and L2, I don't think we are going to be, since we have kept it on both sides, let us just set L1 is equal to L2, that is small simplification then. So let's set L1 is equal to L2, magnitude of L1. And let's say that's L. Okay. In that case, this whole thing becomes a squared quantity, and log of a square brings out a 2 there, right? So this is z hat mu naught I over 4 pi. Mu naught over 4 pi is always comes in that structure, so I don't want to cancel that 2 with that 4 pi. And that's L over, and I also wanted to invert that. So this is minus now times rho over 2L, because 4 is 2 squared. Okay, so remember, log of 1 over x is log of x raised to minus 1, which is minus of log of x, right? So that's the minus sign, and log of x squared is equal to 2 times log of x. So those are the identities. That's your vector potential for for a for a straight line, straight wire, and where rho and z are very close to the wire. We don't want to be very far away. Okay. What's the direction of this? Notice that this is in the direction of the current itself, because current is all in the same direction everywhere. So they all add up and it's in the same direction. It goes down. So as you get closer to the wire, no, does it go down? Yeah. What is the dependence? Because it's long, right? So you should be careful. And that is one of the reasons again that it shouldn't grow out. So yeah, we need a quiz, right? So here is a quiz. Right. Draw. You can plot this, right? First draw field lines of A, or that's the first part, and the second part is plot. So this is a plot, magnitude of A. Magnitude of A is basically remove the z hat with respect to rho. So that means by plot I mean you want this to be rho, that's your A. And by field lines I mean like electric field lines or whatever they are. So that's a good exercise. Okay, so that's what we have. Once we have that, we can actually calculate B, right? We have two ways of calculating B. You can actually calculate it starting from so this is one way. You can start from the Biot-Savart law. This is J R prime crossed with R minus R prime over R minus R prime. Right, that's one way of doing this. And it will turn out, if you were to attempt on this, it will work out that it does not depend. What do you mean? It does not diverge, right? This quantity diverges, notice, in the sense that if L was very large, then it diverges. If the length of the wire grows, then a logarithm of a infinite quantity is infinite. So that's not very comfortable in the sense that as you go along, it seems like it grows. But if you stay close enough, you're good. But the magnetic field doesn't have those features, doesn't have any issues. What is the answer for the magnetic field due to a straight line wire? Infinitely long wire? Magnetic field? As a simple expression?
Mu naught I over 2 rho.
Good. Times it is 2 pi rho, so I'll write that 2 here, right? Just so that you know. And the direction is circular, so it is phi hat. Okay, so that is a very simple expression, no divergence, no information about L. So if we take the limit L tends to infinity, it all goes away. So magnetic field is nice. So let's see how it comes to be. And if we do this integral, I'll encourage you guys to do that. I won't do it here. It goes through exactly the same way, but this is 3/2 now. Right? So here, I think they don't see it. 1, 5. So when we do this integral, instead of this big square root, this is 3/2. And in the numerator, there are some vectors sitting here. Right? Since there is this cross product, so there are some x prime, y prime sitting in there. But that goes through very smoothly. it's sine hyperbolic is not the good substitution. I think sine theta itself is a good substitution. Sine theta or tangent theta might be the good substitution. Okay. So I will not attempt that here. Is that clear what I suggested? Should I say more on it? You would like?
I wasn't talking about, for arriving at B from A, that's what you were talking about?
No, first, there are two ways. Okay,
Mhm.
so let me go back here. So there are two ways of calculating B. One is just take the A and take a curl of it. So let's say this is method 1 and that's method 2, right? I'm going to do method 2 because it's shorter method. We have spent time on A, which is the harder one, like which you haven't seen in introductory physics courses, A. So, and I'm going to calculate B using that. Second is directly use BSL. You do that, maybe you don't write this J density here, but in some form in all the introductory level courses, that's what you do. And there the substitution is not sine hyperbolic theta that we did. A more convenient is tangent theta. Right? That's more convenient substitution to do. Any substitution, many other substitution you can do, but which I'm not going to do here. Right? But I expect you guys to know that. So once I don't do it here, then a good candidate is exam and other things. And something good to ask because I expect. Okay. So, but it should give the same answer. So let's take the curl of that quantity. So this is curl of curl of A is minus z hat. So pull out the minus sign, z cross. Right? So the curl vector crosses with the z hat, and but the gradient also acts on all the quantities inside, right? So it is mu naught I over 4 pi times 2 times log of rho, and let me write that as log of rho over 2. Okay, so the parenthesis tells that this gradient has to act on everything inside, right? Especially, what does it act on? It only acts on rho, right? That is the only quantity that is actually there, which has any variation with respect to the gradient. Okay, any questions? Okay, so as far as the vector part goes, I can switch this, right? Because z comes out of the gradient. Z hat doesn't depend on the gradient, so I can pull it out. When I pull that out, the cross product has switched. So that changes the sign. So this is z hat crossed with the gradient. And these are all numbers, so I can actually pull that out too. Mu naught I over 4 pi, and put a 2 also there. And this acts only on log of rho, if I want to write that, minus log of 2L. Clearly the gradient will not act on 2L, it's a constant. The length of the wire, that doesn't change. So it is simply mu naught I over 4 pi multiplied by 2 z hat crossed with gradient. I'm writing it multiple steps, but it's not a repetitive. It's
So
a constant.
did we lose a negative sign on the?
I use the negative sign to flip z hat, and
Okay.
when I moved it outside, I changed the order of the cross product. Yeah. Okay. This is in cylindrical coordinates, correct? So it is good to write gradient in cylindrical coordinates. So remember, the gradient in cylindrical coordinates will be rho hat times d by d rho plus phi hat, right, that's a cylindrical coordinate phi, 1 over rho times d by d phi plus z hat d by dz. This operator doesn't do anything on log of rho. The operator with respect to phi, the derivative with phi doesn't operate on this. Derivative with z doesn't operate on that. All those give you zeros. It's only the first term that really matters. Correct? So, what do I do? Space. I can squeeze this in. So this is equal to mu naught I over 4 pi 2 z crossed with rho hat times derivative of log is 1 over rho. It's 1 over rho. Okay, is that visible there? Okay, that's equal to again, remember your, what is z hat crossed with rho hat? Like it's good to remember your, so this is a circle, right? That's a cylinder, a cross section of a cylinder. That's your radial direction, right? That's rho hat. Phi hat is tangent. That's your phi hat. And z hat is coming out of the cylinder. So z hat, let's say, is coming out of the cylinder. So that's z hat. Now say z hat crossed with rho hat. Use your right hand rule. So that's phi hat. So this is phi hat. So we have phi hat. That direction comes out correct. It's circular for the magnetic field, and whatever is remaining is mu naught I over 4 pi rho times 2. It is typically written as 2 pi rho, but I'm just keeping the mu naught over 4 pi intact because when you, if you go into another book which is not in SI in Gaussian, then they will write 2I over rho. Mu naught over 4 pi is just gobbled. So in certain books, it will just be 2I over rho if they're using Gaussian. So that's your magnetic field. Okay, so that's good. So let's go back to what we have here. I think the geometry is clear now. Okay. We have B is equal to the curl of the vector potential, and we said A is equal to z hat minus of this 2 times log of rho over 2L, and the magnetic field we said is phi hat I over 4 pi rho times 2. I just rewriting that. Let's go back to this. B is equal to del cross A and see what it means in an integral form. If you have a vector that's the curl of something, I can take like that is the magnetic field in a region. So this could be the magnetic field. Think of an area through which the magnetic field is coming out. So that's your magnetic field that is coming out. And that small tiny area dots with the B there. So this is Stokes' theorem, right? So I'm doing this on a surface S. Let's see that surface S. So how much magnetic field is going through that surface S? What is that called? Magnetic field going through a surface S? There's a word for that?
Flux.
Flux. Right, good.
Can you bring the camera down just a little bit?
Oh. I have to get used to moving the camera. Okay. Remember, A was not unique, correct? We said that A can be moved. You can add an arbitrary constant to A and still magnetic field will not change. But there is something with A which is very standard, and this is, that's first of all, this is the flux, correct? Flux due to the magnetic field in a surface. This is S, the A dotted with B. What is this equal to using a theorem, right? Calculus theorem. What is that equal to? This is
Change it to a volumetric integral.
No. That typically has no something like that. Yes. What you're thinking is d cube r, the volume integral of a divergence, let's say of an electric field, is equal to the surface integral, correct?
Mm-hmm.
So that's the divergence theorem. But this is now something different, slightly different. There is a similar theorem for curl. This is called the divergence theorem. This is the Stokes theorem. What is the Stokes theorem? Stokes theorem says that if you have an area on which you are calculating the curl, so what we're doing is that calculate the curl at every point in this area. But this is a derivative. Usually a derivative contributes only on the boundary. So what's a boundary of an area? That's a line integral. Right. So this is a line integral, but a closed line integral. And forget the derivative. So derivative is like a survives only on the surface. So the flux passing through a surface, of course, can be thought of calculated using the magnetic field, but it can also be calculated using the vector potential. And in this case, this is a measurable quantity. So A itself is not measurable because remember, in what sense is A not measurable? You can add A prime. You can add a, let's say, lambda, some arbitrary function, which is a total derivative you can add to that, but and still your magnetic field remains the same. But this doesn't change this because this is a total derivative, right? When you go around the loop on the boundary, this will go away. Like this will not contribute. So this is unique. So vector potential has some features that you can actually still measure. So, and that is that total line integral of a vector potential can be measured. So it's not that everything associated with the vector potential is useless, right? So that means that now that we have a vector potential for at least one example, we have it for a line current or a current carrying wire, straight current carrying wire. It's a good exercise to actually calculate your A dot dl for some surface area. And that's part of your homework. So I'll give you what it is. So let's do this. So this is a long current carrying wire. Where is the magnetic field of this? This is the I. Right. Everywhere on the right hand side, the magnetic field is going in. And so it has to be a little farther out. It gets weaker as you go out, right? So the density of the lines tells you how weak it is. So as you go farther, they're farther and farther. On the left hand side, it is coming out. Is that clear? I think hopefully that should be clear what that means. That's your magnetic field lines. These are basically circles, like they're going around in there. I want to choose an area. I can use any area in principle, but I want to choose an area which is convenient to calculate things on. So let me choose a rectangle, because magnetic field will be then perpendicularly coming out of it. So let's choose a rectangle here like this. That's a fixed surface now. And now I will specify this rectangle. That's your row 1, that's your row 2, that's your Z2, like height, right? So this is your Z1, and let's just say this is Z2. So the height here, right? So that's your H is equal to Z2 minus Z1, and row here is row 2 minus row 1 could be your horizontal distance. Okay. And you can calculate your DL dotted with A here, or actually, I'll leave that to you. Like you have to actually do this for this line, do that for that line, do that for this line, and so on. But notice that A is in the direction of Z. Right? For us, A is Z hat. Right? So when you take the dot product of this, and Z is in this direction, it's only these two lines that contribute. Right? This is perpendicular to that, that doesn't contribute. So you just have to do this line integral. It's pretty simple, like that integral comes out reasonably easy. But now, once you have that integral done, right, that will give you actually the flux. That's a standard result. But now, if you have a loop, I can have more than one area enclosing that. So this is surely one area, right? But now let me pluck that, stretch that area out. Think of topology, right? You're actually stretching that area out with the fact that that ring, the boundary is kept intact. That's also a surface, perfectly fine. I can pull that out, go all the way here, bring it out here and keep it closed there. That's also perfectly fine. I can stretch my boundary wherever I want to, and I'll still get the same answer. Right? It's harder to prove because the moment you stretch it out, those integrals may not be easy. But I want you guys to appreciate that I can actually stretch this volume out, or sorry, area out, and still get the flux exactly to be the same. Right? It is like saying the fact is like when you say there is a water going in, whether I put my bucket like this, right, or like this, correct? As far as or I have to keep this fixed, right? So I can actually have a bucket like this. It doesn't matter because the opening angle is exactly the same. So as far as his mouth is intact, that is where the water is coming from. That is all it matters. How deep the bucket is doesn't matter how much you're capturing, how much water is going to get into it. Depends only on the mouth of the bucket. And Similarly here, it's only the mouth of the bucket that matters, and in that sense, flux has this connection with the curl in magnetic field, right? So that plays an important role. We will see later on more counterintuitive examples there, especially for Dirac string and so on. We will see that that is interesting stuff.
So practically, do we lose information if we're just, we only have information about the, like the bisection of some surface?
No, we do not lose information. For an arbitrary vector field, yes, you might. But if this equation is valid, B is equal to del cross A, right? Whether you do it left-hand side or right-hand side, you don't lose information. This is pretty much the same as this. Like I try to always emphasize this. If you have an integral, right? So let's say there is an integral dx, d by dx, like here it comes out a bit trivial, right? There is a function of x, and it goes from A to B. If I'm integrating over a derivative, this will be equal to f of b minus f of a. Only at the boundary it will contribute. All the inside ones will cancel out always. Correct?
Mm-hmm.
It's the same thing that is happening here. Usually how you will say this is that there is an area, you're taking a curl in small pieces. Right? Is that clear? Maybe I should draw bigger boxes. Right? When I go the opposite way, this cancels out. Is that clear what I'm saying?
Mm-hmm.
Like all these boxes inside will cancel out, and it's only the boundary that will survive. It's exactly the same thing that is happening here. So I can do a surface integral of a vector field. If it is of the form of a curl, that means it is having some derivative structure in there. It's only the boundary that matters. It will always matter. So you're not losing any information, which is the remarkable part. The surface has the information about the whole function if the function is of this kind.
Okay.
So curl is some kind of derivative, not a normal simple one-dimensional derivative, but it is a derivative. So somehow things cancel out, and this part works out. Helps.
Mm-hmm.
So your homework has to deal with calculating this, appreciating that, and also to, so starting from your B there, you have to calculate the divergence of B and curl of B. What will be the divergence of B for a straight wire?
0.
Just take only 1 minute.
It should just be 0, right?
Always, yeah. Divergence of B is 0, Maxwell's equation, right? But it has to be 0, you have to verify that. So start from the expression for the magnetic field for the wire and show that it is 0. And curl of B, using Maxwell's equation in magnetostatics, is the current density, right? So you should get that current density. You have to start from your answer and then get the current density. So that's the
Right.
few problems that's in your homework.
It was due today also.
But that was not for a wire, right? There you did a very general expression. Now you have to start from this, the wire solution, and do that. Does that make sense?
Yes, yes, that does make sense. I was confused, yeah.
Like you use this expression and verify that. Here you use this expression.
Yeah, okay.
The places where I'm pointing to, I think online it is hard to see.
No, but we know where it's at on our notes.
Okay, good.
We click down, it's right there, right above at 5.
Good. Okay, that's all.
Yeah, it is kind of funny because we knew exactly where you were pointing to.
Oh, really? So you guys
Yeah.
did know. Okay.
Yeah.
As
Okay.
long as you're pointing in a direction, you shouldn't have to always move the camera if you're referring to something.
Okay. Okay. I was really thinking, okay, I'm talking to blind like, for 4 people, and it's only Rob and Moses that's understanding. Okay, good. Okay, I'm glad. Okay, so it's not hopeless to do this. Huh?
Yeah, I mean, when you pointed there, I just looked at my notes, just thinking, just, oh, this is what he's talking about.
Interesting. Yeah. Okay.
Yeah. It takes me an extra second to process, but I can still follow.
But it's much
I
better
know.
than looking at the board at the view we have
This way.
currently. Yeah,
Yeah.
doing it much
Okay.
closer. Because while I can read everything, it's difficult sometimes, I guess, without hearing you say exactly what something is. Like when I'm looking at that step function and I'm looking at L right here, the first L, is that a 1? Is it? I know it's a 1 now because we did it, but if I was just looking at it and I didn't hear you say L1, I'd be like, okay, well, the L2 kind of looks like an L theta from here, but I'm not sure.
Sometimes an LZ.
LZ, yeah. So either L1 or LZ, yeah. In this course, all that comes about. Yeah. Right. Yeah. I think these are because I have never sat in a course like this, so I miss on this. Actually, I shouldn't say. I have done this in collaborations, but then, as you guys are saying, I know exactly what is going on. In fact, I am doing it myself also. Yeah. So, yeah. Okay. Okay, that's all.
Okay,
Yeah, enjoy, guys. Yeah.
Yep. Thank you very much.
thank you.
So I should.
Oh, I wanted to buy.
Yeah, you want to say something? No, she was not telling us.
Okay,
Hey, Luke, is Quantum gonna be on the virtual classroom, or is he? He said something about going to this room.
Oh, for today, I assumed it was virtual again today, but I guess I don't know.
I'm not sure either. I guess we'll see if there's a tab for the next lecture.
Yeah, I can look.
So on D2, it shows up as a tab.
Yeah, there's like, it's supposed to record them.
Got it.
And so you have each lecture day by day. But
Actually, that's an advantage in D12. When you do use those features, then automatically it's recorded. The organization parts is very easy. Here I had to go back, download this on my computer, and then upload it back on YouTube. There is a feature Echo in which is our university has, which automatically records this, and I can give a link to that. I just don't like it. Also, I prefer this because I'm afraid that down the line, 3 years down the line, they'll change the license, and then I'll have to manually move all this again somewhere. So I don't want that headache. So this is YouTube is my area, and I know that no one is going to change the license unless YouTube dies. Like they do something to YouTube. That doesn't seem likely.
What if we get hit by like a big, huge solar flare and changes all the frequencies that we hear at? What will happen with YouTube?
Yeah, I would expect that the servers are backed up. I hope so. Surely I'm not keeping copies because these are 2 big files. For some time, I think until fall, I kept it. But then my somewhere in December, there was only 1 GB left. So the first thing I did.
I was making a joke in reference to like if the frequencies that the human ear hears at changes because of like some maybe the coronavirus, the new version of it changes the way that we.
I see.
And then the Fourier transforms, on YouTube, we won't be able to hear anything. We'll just be able to see it.
Oh, you meant that way, the Fourier transform.
I just have to do an inverse Fourier
Yeah.
transform, and then
But then they just have to rescale that somehow, right? Probably they just have to, a small tweak might do it. Yeah, I don't know. Yeah, but then the older ones might not be done. Yeah, so that will be a inconsistency, I suppose. Yeah, yeah, that's a. Yeah, I didn't understand the joke first, the context.
All right.
You have to high tech. Okay, enjoy, guys.
Rob.
Yeah, Rob,
let me know if
I
you-
do.
Oh, go ahead. Sorry.
Yeah,
Rob?
just I do see a link on D2L for class today, so I think
Okay.
it's online.
I was saying,
the
as soon as
virtual
you-
president
When you talk to
is the
Tori,
most possible product I've seen.
That's a pretty rough evaluation.
Yeah.
Well, see, I fought getting rid, I fought to get rid of D2L at our school.
Oh, really?
I was a real pain. I started teaching Canvas before we'd adopted it.
So what was the option you had other than D2L? What are the other candidates?
Well, we had Blackboard, but they didn't want to use it because it's expensive.
I see.
But what they found out is D2L did cheap, but then that's, it's kind of like you're getting the base model.
I see.
Whereas some of the other ones, they were giving you the really nice tricked out model. So somebody Canvas would let individual faculty members have a space to do their classes, but they just had limited storage capacity and stuff like that. So I was using it for years.
I see. I see.
And every time I tried to use D2L, I decided that there was not enough whiskey in the world for that. And I went back to Canvas.
So you went back to Canvas.
I kept on trying it and saying, maybe they've improved it, because I keep on getting these emails saying, oh, they've upgraded it, they've made it better. And what they really did is they made it look more like Canvas
I see.
without the functionality.
So you don't have to have license for Canvas?
You can operate it as an individual
I see.
for up to like 6 classes, I think, or something. There are limitations,
I see.
but my school adopted it, so I don't have limitations.
Okay. Okay.
But one real simple thing. I mean, when we do, unless we import everything from a shell that's already created, it's like, if I create a lab graded assignment, you have to put it in so many different spots and click the right buttons in the box. Canvas, it's like, make it, save it, publish it, and you're done.
So, yeah.
When it shows up, you can, and they are very good about drag and drop. And if you make a mistake on your calendar, drag it over and it changes all the dates.
Got it.
That is nice.
Yeah.
Well, everybody have a great day.
Yeah.
Thank you. Yeah, you too.
See you
I
guys.
have used it only for grades. They did.
Only for grades.
Yeah. Till now, yeah.
That's what ends up, when it's difficult, people don't use, you're not getting their money's worth out of the LMS because everybody's staying away from it because it is overly complicated.